Hi everyone. In this lecture, we are going to discuss the Raman spectra. In the last few lectures, we have discussed rotation spectra, that is the microwave spectra, and the vibration spectra, that is the IR spectra. So let us discuss the Raman spectra. So here Raman spectra. So here all of you know that when the substance is irradiated with the monochromatic light, the scattered light is observed in all directions. And here the scattered light, it can be observed conveniently in the direction right angle to the incident light. And it is found that the frequency of the scattered light was the same as the frequency of the incident radiation. So here friends, when the substance is irradiated with the monochromatic light, the scattered light is observed in all direction. And here what is the important? The frequency of the scattered light was the same the frequency of the incident light. The scattering of the light without change in frequency, it was observed by the Rayleigh, and the phenomenon is known as Rayleigh scattering. So here in the spectrum, frequency of the line such obtained is called as the Rayleigh frequency. So here the frequency, it is called the Rayleigh frequency. In 1923, theoretically, the Schmeckel predicted that if the substance in the gaseous, liquid or the solid state is irradiated with the monochromatic light, once again the scattered light should contain radiation with different frequencies other than the frequency of the incident light. So here theoretically in 1923, Schmeckel predicted this thing. But in 1928, the Indian scientist Sir C.V. Raman found that when a beam of monochromatic light was allowed to pass through the substance, the scattered light contains some additional frequencies other than that of the incident light, and this scattering is referred to as the Raman scattering, and the phenomenon, it is known as the Raman effect. So here in this lecture we are going to discuss the Raman spectra. So here in 1928, C.V. Raman found that when the beam of the monochromatic light, when it was allowed to pass through the substance, the scattered light contains some additional frequency other than the incident light, and this effect, it is called as the Raman effect. So the line at the incident frequency is called as the Rayleigh line. The pattern of the big lines on both sides is called the Raman spectrum. So here at the center there is a Rayleigh line, and here the pattern of the big line on the both the side, it is called the Raman spectrum. Here the line whose wavelength are greater or the frequency is lower than the incident one. So here the line whose wavelength are greater than that of the incident wavelength are called as the Stokes line, and those having the shorter wavelength are called as the anti-Stokes line. So here there are two types of the line, that is the Stokes line and the anti-Stokes line. So in case of the Stokes line, the frequency is lower than the incident one, while in case of the anti-Stokes line, the frequency is higher than the incident one. So here the two types of the lines are observed, Stokes and the anti-Stokes line. So here if nu I is the frequency of the incident radiation and nu s is the frequency of the scattered radiation, then here the term Raman shift, that is the delta nu, it is defined by the equation delta nu is equal to nu I minus nu s. So this is the definition, mathematical definition of the Raman shift, and here the Raman shift, it is given by the equation delta nu is equal to nu I minus nu s. Nu I is the frequency of the incident light, while the nu s, it is the frequency of the scattered light. So the Raman shift is characteristics of the scattering substance. So here it does not depend upon the frequency of the incident light. And here for the Stokes line, this Raman shift, that is the delta nu, it is a positive, and for the anti-Stokes line, this delta nu is negative. So the intensity of the Stokes line is always greater than corresponding the anti-Stokes line. So here in Raman spectra, when we compare the intensity of the Stokes as well as the anti-Stokes line, here the observation is that is the intensity of the Stokes line is greater than the intensity of the anti-Stokes line. So here the Raman shift delta nu generally lies within the far and the near infrared region of the spectrum. So here this is about the scattering of the light as well as the Raman shift. Then here when we consider actual Raman spectra, so here this is the Rayleigh lines. So here the frequency of the incident light is equal to the frequency of the scattered light. So here the two types of the lines are observed, Stokes lines and the anti-Stokes line. So here in case of the Stokes line, the frequency of the incident light is greater than the frequency of the scattered line, while in case of the anti-Stokes line, here the frequency of the incident light is less than the frequency of the scattered line. So here Stokes and the anti-Stokes line, here again Stokes line and the Rayleigh lines. So here the Raman shift, again the modules of the difference, that is a nu s and nu I minus nu I, is called as the Raman shift. Already we have discussed the what is meant by Raman shift. So here this is the Raman spectra. Then here the mechanism of the Raman effect. So here the first point is the polarizability of the molecule and the Raman effect. So friends, here all of you know that when we consider the rotation spectra as well as the vibration spectra, so in both the spectra, the molecules which having the permanent dipole moment or only the polar molecule, they are the rotation active as well as the vibration active. That means here they are the micro active as well as the IR active. So here when we consider the Raman spectra, which molecules are the Raman active? Which molecules give the Raman spectra? The molecules whose polarizability changes. Only such molecules they give the Raman spectra. So here let us consider when an electric field is applied to the molecule, its electron and nuclei are displaced. All of you know that when we apply the electric field to the molecule, so what happen here? The electrons and the nuclei they are displaced. That means here electrons they are attracted to the positive plate, while the nuclei it has the positive charge or it contains the positive charge. So the nuclei are attracted toward the negative plate. So here we can say that when electric field is applied to the molecule, its electron and nuclei are displaced. Similar way here, thus when the molecule is subjected to the radiation of the definite frequency and allowed to interact, each molecule experience variable electric field of the radiation, and due to this an induced oscillating dipole moment is produced and the molecule is said to be polarized. So here when the molecule is subjected to the radiation, at that time here induced oscillating dipole moment is produced and the molecule is said to be polarized. Such an oscillating dipole emits the radiation of frequency which is the same as its oscillating frequency. So here this explains the phenomenon of the Rayleigh scattering. Here we have not considered the vibration and the rotation of the molecule. So here this is the Rayleigh scattering. However, when the vibration and rotational motions are considered, this vibration and rotation may change the polarizability. So here during the vibration or during the rotational motion, the polarizability of the molecule changes. Thus, the existence of the Raman lines depend on the change in the polarizability with the vibration and the rotation. The corresponding spectrum is called as the vibration Raman spectrum or the rotation Raman spectrum. So here which molecules are Raman active? Hence, the molecule will be Raman active only when its polarizability changes during the vibrational and the rotational motion. So, this is the condition to obtain the Raman spectra. The molecule whose polarizability changes during the vibrational and rotational motion, only those molecules they are the Raman active or they give the Raman spectra. So, here mechanism of the Raman spectra. So, here this is the vibrational energy state. So, here 0, 1, 2, 3, 4. These are the virtual energy state. So, here infrared absorption, that is IR absorption. This is the Rayleigh scattering. Here the frequency of the incident light as well as the frequency of the scattered light, both the frequencies are same. So, here delta nu is equal to 0. Here the Stokes Raman scattering. So, here in case of the Stokes Raman scattering, delta nu it is less than 0, while in case of the anti-Stokes Raman scattering, delta nu it is greater than 0. Delta nu it is the Raman shift. So, here for the Stokes and the anti-Stokes line. So, here the mechanism of the Raman spectra. So, here there are three conditions 1, 2 and 3. If both the frequencies are same, all of you know that it is the Rayleigh scattering. Then here Stokes as well as the anti-Stokes scattering. Then mechanism of the Raman effect. According to the quantum theory, the incident light can be considered as a stream of the particles called as the photons, each having energy h nu. So, here the photons energy, it is denoted by symbol h nu. H is the Planck constant, nu is the frequency of the light. Then here these photons are supposed to undergo collision with the molecule. If the collisions are perfectly elastic, there will be no exchange of energy between the molecule and the striking photon. So, here if there is no exchange of the energy between the molecule and the striking photon, so here this indicated the phenomenon of the Rayleigh scattering. So, here however, some collisions may also result in the exchange of the energy during the collision. That means here during the collision there is exchange of the energy between the molecule and the striking photon. But here if there is no exchange of the energy between the molecule and the striking photon, then such a phenomenon, it is the Rayleigh scattering. When photons strike the molecule, it gains excess energy from the photon and convert into the energetically excited state. So, here once again, when the photons strike the molecules, that means here when the light radiation, when it falls on the molecule, so here it gains excess energy from the photon and convert into the energetically excited state. There are three possibilities for this excited molecule. So, let us consider one by one. The first possibility, the molecule may return to its initial state where it was before collision. So, here there is no exchange of energy between the molecule and the striking photon, this corresponding to the Rayleigh scattering. So, here this is the Rayleigh scattering. So, here there is no exchange of the energy between the photon and the molecule. So, here the initial and the final state, both the states are same. So, here this is the first point. Second one, if the molecule was initially say in the lowest vibrational energy level, that is V is equal to 0, the molecules gain some energy and scattered photon will have lost some energy, represent the Stokes line. So, here this is the representation of the Stokes line. So, here V is equal to 0, here V is equal to 0. So, here the molecule gains some energy, so photon lose energy, and here we get the Stokes line. So, the Stokes-Raman scattering, this is the second condition. Then the third one, the last possibility or the third possibility is that the molecule which is initially in the higher vibrational level, that is V is equal to 1, before the collision, and will after the collision what happen, will after the interaction with the photon come to the lower energy level, that is V is equal to 0. The energy lost by the molecule is gained by the scattered photon and it represents the anti-Stokes line. So, initially the molecule initially in the higher vibration level, that is V is equal to 1, and finally it is at V is equal to 0. So, the energy lost by the molecule is gained by the scattered photon. So, this is the third condition. So, here V is equal to 1 and here the V is equal to 0. So, here this explains the anti-Stokes line or the anti-Stokes-Raman scattering. So, the Rayleigh scattering, Stokes scattering as well as the anti-Stokes scattering. So, the mechanism of the Raman effect. Then here the selection rule. So, the selection rule for the rotation Raman spectra, it is the delta J is equal to plus minus 2. So, this is the selection rule for the rotational Raman spectrum. The transition delta J is equal to plus 2, it gives the Stokes line, while delta J is equal to minus 2, it gives the anti-Stokes line. So, here this is the selection rule for the rotational Raman spectrum, delta J is equal to plus minus 2. So, let us consider the vibration Raman spectra, and here the what is the selection rule for the vibration Raman spectra. So, here the vibration Raman spectra, the allowed transitions are delta V is equal to plus minus 1, delta V is equal to plus minus 2, delta V is equal to plus minus 3. So, here this is the selection rule for the vibration Raman spectra. So, friends, this is about Raman spectra, then the mechanism of the Raman spectra. So, here when we consider the Raman spectra, three types of the lines are observed: Rayleigh lines, Stokes line as well as the anti-Stokes line. And here during the vibration motion or during the rotation motion, if there is a change in the polarizability of the molecule, only such molecules they are the Raman active. Then next point is the application of the Raman spectra. So, here there are various applications of the Raman spectra. So, let us consider one by one. If the rotation Raman lines are resolved, molecular parameters such as the bond length and moment of inertia can be determined. So friends, again, all of you know that when we consider the rotation spectra for the diatomic molecule, and from the rotation spectra, it is possible to find out the bond length and moment of inertia of the molecule. Similar way, here if the rotation Raman lines are resolved, here we can find out the bond length and the moment of inertia. Then the second one is, while only vibration Raman lines are observed, knowledge about the symmetry of the molecule can be obtained from the vibration Raman lines. Then third one is the rotations and vibrations of heteronuclear molecules can be studied in both the IR and the Raman spectroscopy. So here the rotation and the vibration heteronuclear molecules can be studied in both the IR as well as Raman spectroscopy. This is the third application. Then here the homonuclear molecule, that is H2, N2, O2, Cl2, etc. They are the neither IR nor microactive. So once again here these molecules are the non-polar molecule and they do not have the permanent dipole moment, and all of you know that if the molecule is non-polar, it is a micro inactive as well as it is a IR inactive. But here they give the Raman spectra. So here this H2, N2, O2, Cl2, they are IR as well as the micro inactive, but here they are the Raman active. So here they give the Raman spectra as the polarizability changes during the rotational motion of such molecules. So again here just to obtain the Raman spectra, what is the condition? During the rotational motion or during the vibrational motion, there must be change in the polarizability of the molecule. So this H2, N2, O2, Cl2, during the rotational motion, there is a change in the polarizability of the molecule. So these molecules are the Raman active. Then here the structure of the carbon dioxide, then H2O, N2O can be explained by the use of the Raman spectra. So here many problems of physical chemistry such as the electrolytic dissociation, hydrolysis and ionic equilibrium in solution can be studied by using the Raman spectroscopy. This is the fifth application. Then here the last application, that is the Raman spectroscopy provides information regarding the nature of the bonding, the presence or absence of the specific linkage in molecule and study of the isomers, etc. So these are the some important application of the Raman spectra. And the last point, the difference between the Raman spectra and the IR spectra. In the first column there is a Raman spectra, in the second column there is a IR spectra. So what is the first point? The method is very accurate but not sensitive. So here when we consider the Raman spectra, the method is very accurate but not sensitive. IR spectra, the method is very accurate and the sensitive. Then second point is, it is due to the scattering of the light by the vibrating molecule. It is the result of absorption of light by vibrating molecule. In case of the IR spectra, it is the result of absorption of the light by vibrating molecule. Third point, the vibration in the Raman is active if it causes a change in polarizability, and the homonuclear diatomic molecules are the Raman active. Here vibration is IR active if there is a change in dipole moment, and homonuclear diatomic molecules are the IR active. Already we have discussed this point. Then fourth one is this Raman spectra gives an indication of the covalent character in the molecule. So here this IR spectra gives an indication of ionic character in the molecule. Then fifth point, water can be used as a solvent. So here water cannot be used as a solvent in case of the IR spectra. And the last point, can be obtained for a compound in all three states, that is a solid, liquid and the gaseous substance. They give the Raman spectra, while IR spectra are quite diffuse in case of the liquid and the solid state. So here when we consider the IR spectra of the gaseous substances, so here we obtain the good IR spectrum, but here if the substance is in the liquid state or the solid state, so here we get the diffuse IR spectra. So here these are the some point to differentiate between the Raman spectra and the IR spectra. So the friends, in this lecture we have discussed the Raman spectra. Thank you.